มารู้หน้าก่อน
ได้ค่ะยังไงเดี๋ยวหนูทักไปนะคะอาจารย์สวัสดีค่ะสวัสดีทุกคนค่ะ
สวัสดีครับ
อันนี้มันเป็นสัมมนาที่เราจะเตรียมไว้เทอมหน้าใช่ไหมหรือเทอมนี้
สัมมนาเทอมนี้ครับอาจารย์
เทอมนี้นี่ว่าเมื่อไหร่นะ
สัมมนาผมพูดวันจันทร์ตอนบ่ายครับวันจันทร์นี้
โอ้ผมติดสอบใครสักอย่างนี้ใช่ไหมเนี่ยวันจันทร์เนี่ยเดี๋ยวดูก่อนดิ
ติดแก๊กครับ
แก๊กสอบอ่ะ
ครับผมเริ่มเลยนะครับครับ Good morning everyone my name is Saknarin Channark today I would like to present
ถ้าเราจะภาษาอังกฤษเราเชิญต่างชาติด้วยก็ได้นะงั้นอ่ะ
ไม่เป็นไรครับขอบคุณไทย I would like to present seminar on the topic on progressive and iterative approximation method with memory for least square fitting by Saknarin and Widaiwang. This outline for today. We start with reference that I have in full reference that I focus on both reference on a progressive and iterative approximation method with memory for least square fitting in 2019. Next section is motivation. From the figure 1, you can see lots of blue points where it is looks like one of music notation. Generally, if we need to create a curve of the music notation, the first method that we think about is interpolation. However, this method takes a long time. To improve the speed of this method and so also make the fitting result hold this same shape, researchers consider the way of reduce the number of points for curve fitting. From this figure, there is a blue point set of 205 points. Anyway, we choose only 22 points green for curve fitting like this. Then the result got red curve, which looks like the shape of the blue points. And if we do some process with the green point at step 10, the result of the red curve will be better fitting efficiency than initial fitting. In the fitting result, you can see that the red curve is closest to a blue point set of 205 points. In the same way of surface fitting, a point set of data point which is shaped look like human face. There are lots of points on the human surface. Then we only choose low number of points used in the surface fitting as you see in the figure A. When we proceed the surface fitting until step 4, the fitting result approach to the human face at the first. Then, if we repeat the surface fitting step, the fitting result shows that it is closer to the human face. And next section is preliminary. This section we talk about the mathematical tools. The first is least square fitting, following the reference to fitting data by function from prescribed family of functions lead to the origin of most overdetermined linear system. Let Ti, Bi be a given set of data, presumably presenting some function G at Ti equal Bi, starting with some chosen set of phi1 till phi(n), and let phi be a family of all linear combinations. Phi1 till phi(n) defined like this. And then we want to choose an element of F to approximately fit the given data in this equation. This is system with Aij equal phi j at Ti. And next, we need to find minimizer of Ex from this equation, which you can see this term B minus sigma equal is a square, which we can call fitting data in sense of the square. And next, we need to find argument mean X star, which is error in approximation of the data by function G star. For example, we consider the data in the table 1 and plot it in the figure 3 in the next page. We use a cubic polynomial to fit this data and thus lead to minimizing the expression of EX. From this equation, which is implying the G star T, where it is linear combination of function phi, we define phi1 T equal 1, phi2 T equal T, phi3 T equal T square, and phi4 T equal cubic of T. And the figure 3 shows the plot of data in the table 1, and the figure 4 shows the least square fit of G star T. And we want to know how to find G star. Minimizing EX equal this term is equivalent to finding the least square solution of this equation. Forming the partial derivative of EX with respect each xi and setting this equal to 0, we obtain the normal equation star. It is necessary condition for any minimizer of EX, and it can be shown to be sufficient. If A has length n and A transpose A will be n by n and non-singular, then star has a unique solution. The solution x star of 2 star is called least square solution of the linear system AX equal B. And next is singular value decomposition, which is the important mathematical tool. For given matrix A, we can find orthogonal matrix consists U and V satisfied in this equation, where the singular value sigma I satisfied like this. From the theorem 9.7 in the reference to let matrix A be a real and m by n, which m greater than equal n, define z equal this and c equal this term. Then the solution x star equal u z star of 2 star is given by this equation with z star r plus 1 till z star n arbitrary. When r equal n, x star is unique. When r less than 1, r less than n, the solution is obtained by setting partition arbitrary z star r plus 1 till z star n equals 0. This is also called the least square solution, even though it is not the unique minimizer of norm 2 of ax minus b. Then the maximizer is given by this equation. And this is proof that for orthogonal matrix P with norm 2 of Px equal norm 2 of x, applying this to norm 2 of ax minus b. If we choosing z star r plus 1 till z star n equals 0, it leading to the unique minimum value of norm 2 of x star. And next section is mathematical formulation. For example, we are given a set of data point q1 till qm, and let a point p1 till pm for the fitting data and call it control points. For curve fitting, we choose set of t in the cross interval 0 to 1 so that g at ti equal qi for some function g. We are looking for an least square fitting function approximating g. Analogously, for surface fitting, we choose set of t belongs to unit ball being order lexicographical or Corey, and call set of t is not. From now, we use b1 till bn instead phi1 till phin, which summation of vi equal 1 on the cross interval 0 to 1. It is normalized totally positive or NBT basis of a vector space of real function. For example, this is a Bernstein polynomial basis like this, and the collocation matrix of basis B at the increasing sequence T as follows. And next is a progressive and iterative approximation method. Given a point set Q and chosen control point P10 to till P1 Pn0 from a vector space where Qi is located, we can generate the fitting curve CK plus 1 from equation 1. and we can compute pik plus 1 from the equation 2, where delta ik equal the first line for progressive and iterative approximation of PIA in the reference tree, which n equal m, and the second line delta ik equal this term for least square progressive and iterative approximation in the reference 1. In the figure 5 is curve fitting via progressive and iterative approximation of PIA. In the figure A, Q is a set of data points. In the figure B, we choose control point from P from Q in case of number of P equal Q. We are generate the red curve like this. And next, we need to generate new control point P by adjusting vector of delta ik, where delta ik is different vector for control point. Then we got new control point in pink. After that, we can generate then pink curve.
ฮัลโหลได้ยินไหม
And next, in the figure 6, it is curve fitting via LSPIA method. In figure A, a set of data point is blue, and only 7 control points are chosen as is shown in green point. Then we can generate the first red curve like this. If we need to generate the second curve, it is need to find delta ik, where delta ik is from the sum of different vectors for data points in the group of data point correspond to PIK. Then we got new control point pink. After that, we can generate the second pink curve like this. To increase the convergence speed in this case, the progressive and iterative approximation method for with memory for the square fitting or MLSPIA is present. As usual, the method constructs a series by adjusting the control points and weighted sum iteratively in the equation 3. The first line delta ik equal this term, and the second line delta ik equal this term, where you can see that we use different vector from control point in brown, and the different vector for data point in brown is the second term from the previous curve with R to delta ik minus 1. It is why we call memory for the square fitting. And the third line, delta ik equal this term where k greater than equal 0. From the first line in the equation 3, lambda 1, 0 till lambda m0 are arbitrary points in the vector space where qi till I equal 1 till m is located as in the figure 7. For scalar omega lambda nu, we will choose suitably later. From equation 3, we can rewrite delta ik where in the first line where k greater than equal 1 into delta ik plus 1 in the second line where k greater than equal 0 and equal this term. If we let the term in the bracket equal lambda jk plus 1 like this, then we got the delta ik plus 1 in the equation pink. And form 2, we have a new control point pik plus 1 from the equation 5. Let lambda k, pk, q, and c are column vector like this. Then equation 4 and 5 can be written as the algorithm 6 like this, where h equal this matrix. And from singular value decomposition, the collocation matrix of the basis B equal to this term. And you can see that U and V are orthogonal and sigma R equal this matrix. Let W equal this matrix, which implies this. Then we can imply W transpose H, W equal this matrix, where H hat equal this matrix. And next section is the main results. For the main results, in the theorem 1, under the condition with the weight omega, lambda, and nu satisfy like this condition, theorem 1 represents algorithm lambda k pk converge to lambda infinite p infinite. In the proof of theorem 1, we need the following four results. First is lemma 1. For the lemma 1, we formulate sequence p I k plus 1 from the equation in the first line in the black to the equation in the second line in the color, where the lambda j k plus 1 equals this condition. And next, lemma 2 represents lambda is eigenvalue of h if and only if lambda equal 1 minus omega, or lambda is a root of the one offering equation. And lemma 3 represents both roots of the real quadratic equation are less than unity of modulus if and only if absolute c less than 1 and absolute b less than 1 plus c, and leads to the lemma 4 under the assumption of theorem 1, spectral radiance of h hat less than 1 if and only if omega, lambda, and nu satisfy like this. Since proving the for the proving of theorem 1, since proof that the curve sequence ck generated by the MLSPAA method convert to a least square fitting curve of Q, equivalent to proving that the iterative sequence pk converge to a solution of this equation. So now we will prove that pk converge to a solution of this equation. If beta is a solution of this equation, then transpose of this term is a solution of the equation 7. Let lambda p be any solution of 7 implying this equation. By lemma 4, a spectral radiance of h hash less than 1, which implies a limit of lambda k pk which k approach to infinite, defined equal lambda infinite p infinite exists, which can imply this equation. Thus, lambda infinite p infinite is also a solution of 7 with this condition. By eliminating lambda infinite, we obtain this equation, which means the sequence pk convert to the least square solution, least square fitting result. And we can extend the MLSPAA method to fitting surface. The MLSPAA method approximates the surface iteratively by tensor product surface in the equation 8, where Pij k plus 1 from equation 9 and delta ijk in 10. For numerical results, from 5 examples, you can see that the number of iteration steps of memory list MLSPAA less than LSPAA, and also if we focus on CPU time, you can see that the MLSPAA method use less time than LSPAA, and for maximum deviation at chosen weight, you can see that value of max deviation is very small. And then we can conclude that the progressive and iterative approximation method with memory for the square fitting is developed under the suitable choice of weight will converge to a square fitting result, and that the fastest convergence rate of the method is faster than that of the LSPAA method proposed under the same conditions. Thank you for your attention.